This is the video record for probability in a stochastic process, homework 5, question number 2. The problem setting is we're given a joint probability density function f of x and y, which is equal to 1 over a times y squared times x, and the domain is y is larger than or equal to 1, and x is between 1 over y and y. So the problem asks us to firstly draw the non-zero definition region of f of x and y. Second is to find a so that f of x and y is a valid joint density function. And the third question is to find and draw the marginal density functions of fx and fy. And the last question is to verify whether fx and fy are valid density functions. And this problem can be really straightforward to solve. The first question we draw by drawing a graph and illustrating the domain areas and the two functions of x and y. And we can write it, we can draw it to be like, sketch it to be like this. And since y is larger than or equal to 1 and x is between 1 over y and y, the non-zero definition region of f of x and y is this shaded area where it is above y is y equal to 1, and between these two values where x is equal to y or x is equal to 1 over y. And the second question, we need to find out the value of a so that f of x, y is a valid density function. For it to be a valid density function, we have to find the integral of both x and y is equal to 1. And we first take it the integral of relative to of x, and we can get it to be like this. And the y is from 1 to infinity, and x is from 1 over y to y. And we can get it to be eventually the integral of 1 over a times y squared and times 2 times ln of y, and take the integral relative to y. And if we see the next page, this value should be like this. And if we take ln y equals to be another variable which is w, and then we can find y is equal to e to the degree of w, and the domain of w is from 0 to infinity. And so we can get the final value of this equation is to be like to be here, where it can be derived into by using the principle or theory, by substituting the two parts. It is called integration by parts. By substituting the two parts, we can get the value to be here, and we finally get minus 2 over a times minus 1, which is the value of this integration by parts, and it is equal to 1. So we can easily get a is equal to 2. And for the third and fourth problems, we try to find out the margin density function for both x and y. First, we look at f of y. We just take the integral relative of x of f of x and y, and we can get it to be ln y over y squared. And we're given the domain where y is from larger than or equal to 1 into infinity. And since it is a valid, and we need to verify if it's a valid density function, we take the integral of this fy of y relative to y, and we can get it similarly from the method that we have used in the former question. We can get the density function integral to be equal to 1, and so that it is verified that f of y is a valid density function. And for f of x, and we try to find out the integral of relative to y first of f of x and y, and we need to determine whether x and 1 over x, which one of these two values are larger, so that we can decide which, when we are taking the integral relative to x, we can decide which one of these two values are on the top and which one is on the bottom. So if x is between 0 and y, and we should know that 1 over x is definitely larger than x, so we're taking the integral to find the marginal density function. We find the density in the integral is from x to the value of 1 over x, and we take it relative to y about the function of f of x and y, and this is equal to 1 over 2. Similarly, when x is larger than 1, and of course x is larger than 1 over x, so the marginal density function is can be calculated out by taking the integral to be 1 over 2x squared. And to verify that if f of x is a valid density function, we examine both situations on these two different situations. And as we can see, in neither case f of x is a valid density function, because the integral of f of x during the valid domain area cannot be equal to 1. And this is the end of this second question.